Hey y'all, so today we're looking at these different equations that involve trig functions and we're trying to solve them out. So let's get into the homework here. The main strategy I'm going to use on all these problems, and there's quite a few of them here, is I'm going to try to isolate the trig function itself, and then I'm going to use my good old-fashioned unit circle here to evaluate or to solve for whatever the missing angle is here. So for this first section, we're trying to find all the values of theta. So we're solving for theta. Only on this interval, though. So what's really important here is that we read the directions carefully. Oh, got a little red square there for some reason. This is really what we want to look at here, is this interval. So we're finding the values of theta on the interval 0 to 2 pi. What's nice about that is that means that we only need to identify the solutions that exist on the unit circle. So we're not giving the general solution. I think we got to do that a little bit later here. Yeah, you can see down here it says find all values of x, in which case we would need to give all the values that are not on the unit circle as well. So when we get there, we'll get there, but let's knock out some of these. So the first couple here are very straightforward. There's not really even any solving to do in terms of isolating the trig function because they're already isolated. The first one says cosine of theta equals 0. So what I'm going to do is look over there at my unit circle, and I'm looking to see what angle measures have an x value of 0. Remember that cosine is x. Maybe I'll make a little cheat sheet up here. If you're looking for a cosine, you're looking at the x coordinate. Okay, let me make that a little smaller so I can fit a little bit more up there. So if I'm looking if I'm looking for cosine, I'm going to be examining the x coordinate, okay? If I'm trying to solve one that involves sine, I'll look for the y coordinate. And if I am trying to get tangent, that's going to be the x coordinate, the y coordinate divided by the x coordinate. So when we get there, we'll get there. So cosine of theta equals 0. Again, I'm looking for where the x coordinate is 0, and you can see that's going to happen at pi over 2 and 3 pi over 2, so those are our solutions. There's not really anything to solve here. Let's see, do I have a theta? Oh, nice. Okay. Why is it so big? I must have been using some large font on the last video or something. Okay, that looks a little better. What size is that? 16? Okay, let's just make sure we're consistent here. So yeah, this will be pi over 2 and 3 pi over 2. So we're going to get multiple solutions here. If this were the general solution, we would have to say like plus 2 pi n to indicate that we have infinitely many solutions. They're all separated by 2 pi units, but we don't need to do that here. So there's our solution for number 1. Number 2 says sine of theta equals 1, so we're looking for where the y coordinate, right, look up here, y coordinate is 1, and we see that that happens at pi over 2. So that only happens at one place on the unit circle. There we go. And that's it. So let me go ahead and I guess I could just move it over since we're going to keep needing to use it. Oh, and now I'm gone. There I am. Okay. I might need to shift this up so you can see that part of it too. Okay, so we're trying to solve this for theta. So the first thing we're going to do is subtract 4 from both sides. And that's going to leave me with root 2 times the sine of theta equals negative 1. And from here, we're going to divide both sides by root 2. So I get sine of theta equals negative 1 over root 2. And I do want to rationalize this because as I look around my unit circle, I don't see a 1 over root 2 anywhere in the y coordinates, but when I rationalize this, I will see what I get. So if I multiply this by root 2 over root 2, what I end up with is negative root 2 over 2. Now this is something I do see in my y coordinates, and you can find that at looks like 3 pi over 4 and 5 pi over 4. So I'm just going to steal this real quick. So at 3 pi over 4, and 5 pi over 4. Oh, wait a minute. Let's hold off here. 3 pi over 4 is actually not going to be a solution. I was not looking in the right place. The 5 pi over 4 does work, but not 3 pi over 4, okay? 3 pi over 4, the coordinate I'm looking at that is negative root 2 over 2, comma root 2 over 2. But what I should be looking at for sine is the y coordinate. So 5 pi over 4 does work because that point is negative root 2 over 2, comma negative root 2 over 2. But the other one is going to be 7 pi over 4. So my bad there. Let's go ahead and delete this one. We'll change that to 7 pi over 4. So, wow, glad I caught that. Okay, so let's go on to the next one. Number 4, get rid of this unit circle, says sine squared of theta equals 1/2. So we're going to take the square root of both sides, and that's going to leave me with sine of theta equals plus or minus. The square root of 1 is 1, and the square root of 2 is root 2. And we've seen this already, and this is going to be something that just happens pretty frequently in these problems, is, let me go ahead and hide this. When we have this 1 over root 2, after we rationalize it, we get something that's a little bit more recognizable, which is that root 2 over 2. So what we actually have here is plus or minus root 2 over 2. And so now as we look around the unit circle, let me bring that back. We're looking for whether, any location, any angle measure rather, where the y coordinate on the unit circle is either positive root 2 over 2 or negative root 2 over 2. So now I can actually grab that 3 pi over 4 that I had before, and including all those same angles that I had before, because we already found, up here, where is sine, what angle measure gives us sine theta value of negative root 2 over 2, right? So those are for the negative root 2 over 2s, but we also need to include the positive root 2 over 2s, which should happen in quadrants 1 and 2 at pi over 4 and 3 pi over 4. So we get all those pi over 4s that are on the unit circle. Okay. Those are my solutions for number 4. For number 5, we're going to solve it kind of similar to how we did number 3. So we're going to, over here we subtracted 4, we divided by root 2. Same kind of deal here. We are going to add root 3 to both sides. And that'll give me 2 cosine theta equals root 3. And then we can divide both sides by 2 to get cosine of theta equals root 3 over 2. And then so now we've got our trig function is isolated, and so we can go ahead and figure out, okay, well, what is theta? So I'm going to bring up my unit circle. I'm going to look, say, okay, well, where's my x value, root 3 over 2? And I see it happens at pi over 6 and 11 pi over 6. So theta, just kind of steal one of these, at pi over 6 and 11 pi over 6. Number 6, you'll notice all these ones that are kind of set up in a sort of linear equation. I know it's not exactly a linear equation because you have the trig function, but everything else is solved exactly the same way as you would solve a linear equation. So for number 6, we would subtract 1 on both sides. So subtracting 1 would leave me with negative, not theta, root 3 cosine theta. And that would equal 5 halves minus 1, which would be 3 halves. And then we need to divide both sides by negative root 3, which is going to be a little ugly, to be honest. But after we rationalize, hopefully the whole thing gets cleaned up. So I'm going to divide by that negative root 3. Okay, so that's going to make my fraction negative, first of all. And then dividing by root 3 is going to put that on the bottom there. And so we need to rationalize this. So when I multiply this by root 3 over root 3, what I'm going to get is 3 times root 3. And then down here, root 3 times root 3 would be 3. So 2 times 3 is 6. And so this could be reduced, right? 3 over 6 reduces to 1 over 2. And so we get a nice value here that we should recognize. I mean, you should start to see that you're getting a lot of the same values here for your trig values. You know, root 2 over 2, root 3 over 2, 1/2, all those negatives, 1, 0. I mean, those are really the only ones that I'm going to expect you to know for sine and cosine anyway. So we're looking for the angle measures whose terminal side intersects the unit circle at this x coordinate. Cosine, again, is referring to the x coordinate. So I'm looking around and I see one happening at 5 pi over 6. And let's see, where's the other one? 5 pi over 6 and 7 pi over 6. So 5 pi over 6 and 7 pi over 6. Okay, so there's number 6. For number 5, let's get this unit circle out of the way. Another one that we're going to solve very similarly. It really doesn't start getting switched up until like 9, 10, 11. We start having to deal with using our quadratic techniques like factoring and things like that. So here we're going to solve for theta by subtracting 9 from both sides first. So I get 5 cosine theta equals, let's see, 4 minus 9 would be negative 5. So if I divide 5 on both sides, I'm going to get cosine of theta equals negative 1. And then so I'm looking for where the x value is negative 1, and that only happens at one location on our unit circle, and that's going to be at pi radians. For number 8, we're going to take the square root of both sides. Now normally when you do this, you would have to put plus or minus. You know, we would get plus or minus and then whatever is the square root on the other side, but the square root of 0 is 0. And whether you try to multiply 0 by 1 or negative 1, it doesn't really change anything. It's always going to be 0. So we can actually ignore the plus or minus for this one. And so now we're looking to see where is sine of theta equals 0. Did we solve that one already? Oh no, we did cosine equals 0. So where is sine equal to 0? That's going to be at 0 and pi. Now, it's also at 2 pi and 3 pi and 4 pi, but remember, we're only giving the solutions that are in between 0 and 2 pi. And if you remember your set notation, the bracket means we can include that. Parentheses means we're not going to include that one. So we're not going to list 2 pi as a solution here. So we're just going to say 0 or pi. Now, number 9 is where things start getting shooken up here, okay? For number 9, we have to factor this. So what I want you to think about as you're factoring this is we've got something squared minus, so I might do this out to the side here just to kind of help my thought process along. I'm going to write this as u squared minus 6u minus 7 equals 0. If it helps, you can write this as x. You know, it doesn't matter what you call it. But basically, you know, I want to be thinking about how does this factor, okay? And I know that this thing factors as x minus 7 times x plus 1 because negative 7 times 1 is negative 7 and negative 7 plus 1 is 6. So that's just like a little trick here is if you're getting thrown off by all the trig functions is to try to factor one that's similar. Okay, but instead of writing like sine of theta, just put x. And sometimes it can be easier just mentally to process what that factoring is going to look like. Okay, so my first step that I'm going to write here now is going to be sine theta minus 7 times sine theta. Did that really do what I thought it did? How did I get that on there? That's weird. Anyway, sine theta plus 1. And so we'll solve these separately. Okay, so, and that's going to equal 0. So we can set each one of these equal to 0. So we'll set this one equal to 0, and this one equal to 0. So we should get sine theta equals 7, right? If I add 7 to both sides. I'm also going to get sine theta equals -1. Now, if you look around the unit circle, this is never going to happen, right? Because the largest number that the sine function ever takes on is 1. So it'll never get above 1. And so since this is saying, when is sine theta equal to 7, you're going to say never, essentially. Like if I bring up Desmos real quick to show you the graph, let me get rid of this unit circle. And if I graph sine theta, and I graph y equals 7, so there's y equals sine x, and what I'm looking for is like, when is this function equal to 7? See, it never is, right? Here's 7. This thing is never going to intersect this graph, right? Because it's way too high. So when that happens, this does not produce any solutions, okay? So from here, you would say there's no solution here. Now, there is a solution overall because this one has a solution. So we're going to say that theta is equal to the angle measure where sine is -1, which is when the y-coordinate is -1, and that happens at 3 pi over 2. So this one results in no solution, but there is a solution to the entire equation because our other factor, in other words, like, remember the zero product property says that if you've got two things that multiply to equal 0, at least one of them has to be 0. They don't both have to be 0, okay? Because if I multiply like 2 times 0, I still get 0. So even though there's not anything that will make this 0, as long as this guy over here is 0, then that is going to be a solution as well. So the only solution we get here is this 3 pi over 2. I'm going to include a little note here. If you're just looking at this, I'm going to say that the maximum value for sine theta, am I even going to be able to write theta here? Or I'll just say for the sine function is 1. All right, so the minimum, by the way, is -1, so this is as small as this one will get. Okay, so let's look at number 10. It looks like we got a little bit more factoring going on here. But in this case, we're going to factor out a GCF since we don't have a constant. There's not like a +1 or +7 or -6. There's no term by itself without our trig function. So we're going to solve this by factoring out a GCF, which in this case would be 4 cosine theta. So if we factor that out, we'll be left with 2 cosine theta minus 1. And so we'll just solve these separately. Okay, so again, we're going to split this up using the zero product property in the same way that we split up this, right? We set each factor equal to 0. So we'll set each of these equal to 0, and if I have 4 cosine theta equals 0, and I have, there we go, 2 cosine minus 1 equals 0, then whatever angle measure will make either one of these true is true for the whole thing. So if I divide both sides by 4 here, 0 divided by 4 is just 0. So I'm going to get cosine of theta equals 0. Over here, I'm going to add 1 and then divide by 2. So what I end up with is cosine of theta equals 1/2. And that'd be positive 1/2. So I'm looking for all of the theta values, all the angle measures whose terminal side intersects the unit circle, where the x-coordinate, because we're talking about cosine here, is either 0 or 1/2. So let's bring back that unit circle. Oops. There we go. Bring back the unit circle, and we're going to find where this is. So cosine, the x-coordinate is 0 at pi over 2. Let me grab one of these. So yeah, pi over 2 and 3 pi over 2. That would be for the solutions that to this part. And then we're also looking for where cosine is equal to 1/2. So the x-coordinate, where we're looking for the angle measure where the x-coordinate is 1/2. And so that happens at pi over 3 and 5 pi over 3. So that's it. All right, so now we got a couple tangent ones, which are a little trickier because you got to look at both the x and the y coordinate. But I think we can handle it. So let's start with number 11, tangent squared theta minus 1 equals 0. So we will start by adding 1 to both sides. That'll give me tangent of squared theta equals 1. And then if I take the square root of both sides, I'm going to get tangent of theta equals plus or minus the square root of 1, which is just 1. Oops. So we're looking for where tangent's either positive or negative 1. In order for tangent to be 1 or negative 1, both the x and the y have to be either the same or opposites. So like the only coordinates where that happens is like pi over 4, 3 pi over 4, 5 pi over 4, because look at the x and y coordinates at those angle measures. They're either the same or one's positive and one's negative. So in that case, all of those would be solutions to this equation. So we're actually going to get the same answers we got for number 4 here. And that would be our answer to number 11. Let's get this unit circle out of here. And I don't know what all this stuff is. Let's just delete that. Okay, so for number 12, we're going to solve number 12 similarly to how we solved number 10, where we factor out a greatest common factor. In this case, our greatest common factor is going to be tangent theta. So we're going to say tangent theta times tangent theta plus 1 equals 0. So we'll split this up. Say either tangent of theta equals 0 or tangent theta plus 1 equals 0. So we have tangent of theta equals 0 or tangent of theta plus 1 equals 0. So if we subtract 1 on both sides, we get tangent of theta equals negative 1. And so tangent of theta equals 0 anytime the y is 0, because remember it's y over x. So let's bring this unit circle back. So anytime y is 0, that's going to be at 0 and pi. Okay, so let's go ahead and start typing our solutions here. There we go. So 0, pi, and then tangent's equal to negative 1 whenever the x and y are opposites. So that's going to be 3 pi over 4 and 7 pi over 4. All right, so that's 1 through 12. All of those, you're just writing the solutions that you find on the unit circle. Remember that the directions specifically state to only give the solutions that are between 0 and 2 pi. So if the solutions are not 0 to 2 pi, we didn't write them, but here, we're starting with number 13, we're going to give all of the solutions. So we're going to give every single solution to the equation, including ones that are not on the unit circle. And so we talked about this in the lecture, that the way you do that is basically the same thing that we just did, except you're going to use set brackets around your solutions and then write plus 2 pi n with the implication that n could be any integer. So that way, you basically add 2 pi or subtract 2 pi to find the coterminal angles that will represent all the other solutions to the equation. So for number 13, we are going to start by subtracting 1, and then we're going to divide by 2. I'll do that separately. So 2 sine of x equals negative 1. And we'll divide both sides by 2. So we get sine of x equals negative 1/2. So looking at our unit circle, and I keep bringing that up, but that's really how you're going to solve these, is we're looking for where the y coordinate is negative 1/2. So that would be, let's try not to mess this up like the last one that I messed up. That'd be, looks like 7 pi over 6 and 11 pi over 6. So here's how you're going to write it. You're going to say 11 pi over 6 what did I say? 7 pi over 6. 7 pi over 6 and 11 pi over 6. So these would be the solutions on the unit circle, but since it says give all solutions, we're going to put set brackets around these and then write plus 2 pi n. And that's really all you have to do there. Is just list your solutions that you would normally list like we did above, and then write plus 2 pi n, saying that basically you could take either of these angle measures, add 2 pi or 4 pi or negative 6 pi, and you'll get another set of solutions. So there's infinitely many solutions here, but we're going to write them out like this. For number 14, let's get rid of that. We're going to solve it basically exactly how we did number 13. The only difference is we're going to end up with a root 2 over 2. Didn't we solve this one already? Hold up. I could have swear oh, it was very similar. Okay, it wasn't exactly the same, but we're going to solve it in pretty much the same way. In fact, I'm just going to borrow this whole deal here because it's going to be solved very similarly. Yeah, the first step we're going to do here is we're going to subtract 1 from either side. Okay. Actually, it ends up being the same. Check it out. The only difference between this one and the last one, this is kind of funny, is that you do the 3 minus 4 to get negative 1, whereas here you're going to do 0 minus 1 to get negative 1. That's why I recognized it, I think, because the rest of the work is the same. So you divide by root 2, rationalize, and then start writing your solutions. The big difference here, aside from just this one tiny little difference on how you solve it here, is that since we're giving the general solution, we need to write the general solution appropriately. So we're going to put set brackets around our 2 unit circle solutions, and we're going to write plus 2 pi n, just like we did the last one. There we go. Okay, number 15. Well, we only got a few left here, not too many left. 15, okay, so here we've got a reciprocal function that we need to, that we need to reciprocate. So what we want to do here is we're going to subtract 4 from both sides, leaving you with 3 cosecant squared x equals, let's see, 4, yeah, just 4. And then we're going to divide both sides by 3. So we're going to get cosecant squared x equals 4/3. And now we're going to take the square root of both sides. So we get cosecant of x equals plus or minus. Can't forget that plus or minus. The square root of 4 is 2, and the square root of 3 is root 3. Now don't bother trying to rationalize this yet, because we are going to reciprocate both sides anyway, and it's going to take care of that problem. So what I mean by that is, I don't want to be looking for cosecant on my unit circle. Instead, what I'm going to do is I'm going to just reciprocate both sides, flip both sides at fractions, and rewrite cosecant as its reciprocal, which is sine, and rewrite the right-hand side as its reciprocal, which will be plus or minus root 3 over 2. Okay, oh, that's not our answer, but that's going to be how we get our answer. So whenever you have these reciprocal functions, just kind of wait till the end, and on these you can, if you want, you can avoid trying to rationalize if you just reciprocate at the point where you need to. So now I'm going to look at my unit circle, and I'm looking for where the y values are plus or minus root 3 over 2, and I see one at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So there's a bunch of them. So let me steal one of these solution sets. And so x is going to equal pi over 3 and 2 pi over 3 and 4 pi over 3 and 5 pi over 3. And then we have the plus 2 pi n to indicate that we are going to get every solution, not just the ones on the unit circle. Number 16, we're dealing with tangent, and so we need to subtract 1 from either side. We got another squared one here too. The squared ones always have more solutions. So you got the plus or minus thing going on towards the end. Okay, so here we're going to divide both sides by 3. And then we're going to take the square root of both sides to get rid of this squared. Square root of 1 is 1, and then the square root of 3 is just that. It's the square root of 3. So again, here, don't worry about rationalizing here, because what I'm looking for is, remember that tangent is going to be the y-coordinate divided by the x-coordinate. So what I'm really looking for is a point that where the ratio of y to x is going to be our square root of 3. Actually, I'm not going to be able to write it with that, so I'll do this. The square root of 3, comma, 1, right? Y over x. But this is a ratio, and we're not going to see a point like this on the unit circle. They're all going to be divided by 2. But when I calculate tangent, these over 2's just end up canceling out. So the coordinate I'm looking for here is root 3 over 2, comma 1/2. That's kind of the key here, okay? So we're looking for this point. And you know what? I forgot the plus or minus on this next step. So basically, any combination of root 3 over 2, comma 1/2, where either of these could be negative, they could both be negative, they could both be positive. Because of this plus or minus, we don't need to worry about which one. So we're going to get a total of 4 locations around the unit circle, and then we'll do the plus 2 pi n. So our solution is going to look kind of like this, except we'll get the actual angle measures when I pull up this unit circle. Let's take a look. So where do we get this root 3 over 2, comma 1/2 business? Whether, and it could be plus or minus. Just want to reiterate that. Is let's see here. I see the first one at pi over 6, and the next one at 5 pi over 6. And you'll notice, you'll see this pattern where you have all pi over 6's or all pi over 3's or something like that. So we've got pi over 6, 5 pi over 6, 7 pi over 6, and the last one should be 11 pi over 6. So, it might be worth even throwing in this plus or minus bit over here, just to show that, hey, it doesn't really matter which one's positive and negative because of the plus or minus. So this is what we're looking for. There we go. All right. We only got 4 problems left here, y'all. Okay, thanks for hanging in there with me. Let's take a look at, I think we only got 4 more, yeah. Number 17. Okay. This one's going to be probably one of the harder ones. Let's get rid of that unit circle. Okay. So we've got a problem here. Whenever we got these squareds and we have one that's not squared, we have to try to factor it or do something along those lines. So usually when we're factoring, we want it to be equal to 0 so we can take advantage of the 0 product property. So let's go ahead and rewrite this so that it does equal 0. So I'll have secant squared x minus secant x minus 2 equals 0. And so I can factor this. What you want to be thinking of is the equation. Did I use x's or use earlier? I want to stay consistent here. So I used x's, that's fine. So, but I got x's over here. So I think I'll use u this time. So u squared minus u minus 2. So think about how would you factor this thing, okay? And you would factor it as u. We're looking for 2 numbers that multiply to give me -2 and add up to -1. So that would be positive 1 and -2. Yeah. So that's how we're going to factor this. It's just instead of u, we're going to have secant x. All right, so we get secant x plus 1 times secant x minus 1 equals 0. Oh, not minus 1, my bad, minus 2. Okay, so now we're going to set each one of these equal to 0, and we're going to solve them individually. Okay, over here I get if I subtract 1 from both sides, I get secant x equals -1. And over here, if I add 2 to both sides, I get secant x equals +2. So we don't want to be looking for these on the unit circle, the secants. Let's reciprocate both sides. Okay, the reciprocal of -1 is just -1, which is kind of nice, so I don't actually have to change anything there. And then the reciprocal of 2 is 1/2. So secant, not secant, cosine of x equals 1/2. So we're looking around the unit circle for any time cosine is -1 or 1/2. I think we're only going to get 3 solutions on the unit circle. There we go. Okay. So the first one, let's bring it on up. You know, guys, I don't have these memorized. I got to look at the unit circle every time like you do. Okay, so cosine of is -1 at pi. And then cosine is 1/2 at pi/3 and 5pi/3. And we'll do our plus 2 pi n like we've been doing, and that's it. That's your solution for number 17. For number 18, we're going to start by subtracting 5 from both sides. So we'll have negative sine x equals 6 minus 5, which is 1, and then we'll divide both sides by -1 to get sine of x equals -1. And that happens just at one location at, oh, you can't see what I'm writing here. Let's move that over. Sine of x is equal to -1 at 3pi/2. Oh, but hold on. We're still working with all the solutions, so we need to not move so quickly here. We need to make sure to put the plus 2 pi n. All right, number 19. These last two problems are a little more challenging than the rest, no doubt about that, but we can get them done. So number 19, don't divide both sides by cosine. Okay, you're going to lose out on some solutions if you do that because cosine could be 0 and you're not allowed to divide by 0. So let's subtract instead cosine x from both sides, and that gives us cosine cubed x. Ooh, how about that? Minus cosine x equals 0. And what we could do here is factor out a cosine x as a greatest common factor. And then we'll solve each of these separately, right? We can use the zero product property like we've done on a few other problems to set each of these factors equal to 0 and then solve them. So cosine of x could equal 0, or cosine squared x will equal 1. So if cosine squared x equals 1, and we take the square root of both sides, we'll get cosine of x equals plus or minus the square root of 1, which is just 1. So it's plus or minus 1. So we're going to have 3 locations here, I believe. Let's go ahead, and I don't want to have to retype this little answer box and all that stuff, so I'm just going to copy and paste this. Hope you guys don't mind that I do that. Don't get too confused. All right, so cosine of x is 0 when x is, let's pull up that unit circle, our good friend. So cosine is 0 at pi/2 and 3pi/2. So actually, we're going to get 4, not just 3. All right, so come on, here we go. So at pi/2 and what was the other one? 3pi/2. And then cosine is either 1 or -1 at 0 and pi. So we have 0 and then just pi. Okay, yeah, that's it. All right, so we get those solutions. The last one, I think, is really more of a, this one's a little trickier, okay? But it's not too bad. You just have to be a little creative in how you solve it. So I kind of like doing this a very unconventional way, just by thinking, okay, well, where is sine equal to cosine? You know, what angle measures have the same x and y coordinate? And you can see that's going to be pi/4 and and 5 pi over 4 are the only locations on the unit circle where that happens. There is a way you could solve this algebraically. I like the sort of conceptual method of just saying, okay, well, when are these two the same? Go around and find when they're the same. You could solve this algebraically if you're uncomfortable with that, and that is, the trick here is to divide both sides by cosine x. Now, this is something we haven't really talked about yet, which is why this is sort of like a bonus problem here. But if I divide both sides by cosine x, this is something we'll get into next time. I think we'll get into next time. This thing right here, sine divided by cosine. Now, how do I evaluate sine? I look for the y-coordinate. How do I evaluate cosine? I look for the x-coordinate. Well, what's y over x? That's actually tangent. So the sort of big secret here is that sine divided by cosine is equal to tangent. And that's something we'll talk about next time. But anyway, now we'll find, where is tangent of x equal to 1? Well, that's where the x and y's are the same. This goes back to the original question, like where are the coordinates the same? Where's x and y the same? That's going to be at pi over 4 and 3 pi over 4. So let's just grab, do we have a good one there? I guess I'll just steal this one. All right, so this would be at pi over 4 and 3 pi over 4. I made a little error here. Tangent of 3 pi over 4 is actually negative 1. It's not 1. If you look at your unit circle, which you can see above, that I've got here, at 3 pi over 4, the x and y coordinates are not the same. So when I divide them, and I'm not going to get positive 1, I'll actually get negative 1. So the two angle measures on the unit circle where tangent of x equals 1, one of them is pi over 4, but the other one should be 5 pi over 4. So I'm going to make that correction here, and the rest of the video is going to have the incorrect answer, but it should be 5 pi over 4 here. And that's it for today, y'all. Hopefully this made sense to you. As always, let me know if you guys have any questions, and if not, y'all have a great day.